Hi and welcome to this video from the series of trigonometry, and in this one we really are opening up the kind of big brave new world of new trig stuff for you guys. And in this one we're going to be looking at reciprocal trig ratios, which is a bit of a mouthful but hopefully is fairly understandable as an idea. But what I'm going to basically do is introduce you to three more ratios. You're comfortable with sine, cos, tan, you've got three more, and as you can see them on the slide there, you have got cot, sec and cosec to be able to deal with. And also we'll have a look at how their graphs work as well. So here we go. Reciprocal trig functions. There's your sine, cos, tan, and coming from the right angle triangle, opposite adjacent hypotenuse. That's the structure you're familiar with. And so if we take the reciprocal of sine, so if we do 1 over sine theta, that would be, well, sine is opposite over hypotenuse. So that would be the same calculation, but the other way up. So we're doing hypotenuse over opposite. And that thing is called cosec. If we take the same principle with 1 over cos, so that's going to become hypotenuse over adjacent. That's sec. And then the final one is 1 over tan, and that one is called cot or cotan. So first thing to notice for this one really plays my brain a little bit, is that 1 over cos is sec. 1 over sine is cosec, and in my head that seems to be the wrong way around. I really want 1 over cos to be cosec, but it's not. So it's yet another one of those little things that I remember as being backwards. For example, when you're doing a horizontal shift of a function, it goes kind of the opposite way to the sine. When you're doing second derivative and you're checking max or min, it's the greater than 0 is the min. Again, back to front. This is another one of those things that just isn't the way around my brain wants it to be. But it is what it is. 1 over sine is cosec, 1 over cos is sec. You just need a way to make sure that you can remember which way around it is. Now, all of that said, let's have a look at a quick question involving these. So we're told that the value of the sec ratio for a particular angle is given to us as minus 13 over 12. And we're told that the angle theta is reflex. So what are the equivalent values of sine and cot? Okay, a couple of ways of doing this, and you will see a different method a little bit later on. But for now, what I'm going to do is stick to my personal favourite of how to deal with these. Is anytime I've got a ratio given to me as a fraction, I draw myself a little sketch of the triangle. In this case, we've got theta is reflex. So we need to be in the third quadrant. And I know it's going to be in the third quadrant rather than the fourth quadrant because we're looking at sec. Sec is 1 over cos, this one up here. So it's the adjacent side that needs to be the negative. And that's the thing that tells me that we're in the third quadrant rather than the fourth quadrant. This third quadrant here is where the adjacent is negative. So what we've got is the hypotenuse is the one on the top. So that's your 13. And the adjacent is the one there. So that's your minus 12. And so we've got a little right angle triangle. Hopefully you recognise 13, 12, part of the 5, 12, 13 triangle from Pythagoras. So we've got the missing side there is minus 5. We know it's a minus because we're in this quadrant here, so that's negative. So therefore straight away we see sine, opposite over hypotenuse, minus 5 over 13. And cot theta, cot we know, or we're told, is adjacent over opposite. So in my triangle, we've got minus 12 over minus 5, which is just clearly 12 over 5, and there's our two values. So that was just a quick little kind of play around with just mucking around with like kind of adjacent, hypotenuse, and opposites and all that kind of stuff in the context of those. So let's say we've now got sine, cos, tan, cosec, sec, and cotan. On we go. Let's have a look at a quick proof question. So in year 2 we're going to get quite a few, you'll see quite a few of these where you've just got to manipulate any of the 6 ratios to prove a particular result. So we've got this fraction here, we've got tan plus cot over sec, and we've got to show that's the same as cosec. So what we're going to do is start off with this expression on the left here and manipulate it until hopefully we end up with cosec. So looking at that, first thing that springs to mind for me is I'm just going to have a scribble over here. Tan theta is sine theta over cos theta. That's our one identity that we had from last year. I'm going to bung the other one down here as well from year 1, which was the sine squared plus cos squared theta equals 1. It might be we need to use that later on. So those are the two facts we've got. Those are the two things that are going to allow us to manipulate. What else do we know? We know that sec theta is 1 over cos theta. And also, you know what, while we're at it, we've got cot theta is going to be the reciprocal of that one, so that's going to be cos theta over sine theta. So those are all the tools that I've got to be able to kind of play around with. So let's see what we do. Right, first things first, I think we are going to end up using the sine over cos, the cos over sine. That'll leave me with fractions stacking up within fractions. So I think the first thing I'm going to do is deal with this 1 over sec theta. Sec theta is 1 over cos. So essentially 1 over sec, which is what we're looking at here, is 1 over cos, if you're keeping up with that. And so that just gives me cos. So the first thing I'm going to do is just rewrite that fraction and write it as cos theta times by tan theta plus cot theta. And that's going to make my life, I think, a little bit easier. Now let's have a go with the old sine over cos is tan, and the equivalent one here, cot theta is cos over sine. So let's bang those in. Now we've got a couple of choices. We can either multiply out the brackets, or we can add those two fractions together inside the bracket. And I think the bottom line is I think we're going to end up in the same place. So I'm going to multiply out. So I'm going to do cos theta times by this fraction here. And that's going to mean those two cos are going to cancel. And then if I do cos times by this one, that's going to leave me with the cos squared on the top. So let's do that. Now I am going to have to add the two fractions together. And so I'm saying two fractions. I see this as two fractions because what we've got here, and let's have a little scribble again. If I've got sine theta and I want to add it to this fraction here, then I need to have a sine theta on the bottom. So at the moment I've got that. So what I'm going to do is times by sine theta over sine theta. So that becomes sine squared theta over sine theta. And so now I've got sine theta on the bottom of that fraction. So that's that. And now we can see, happy days, it's almost like I knew this was coming. There's the sine theta plus cos theta equals 1. There it is appearing on the top of that fraction. And when I add these two together, the bottom will be sine theta, the top will be 1. 1 over sine theta, 1 over sine, as we saw from the previous slide, is cosec. And there we go. Job done. Now, there is more than one way of going at that. You could have done things in a slightly different order, but sometimes things pop out quite easily. Sometimes you have to kind of go back to go forward, if that makes any kind of sense. But the more you do, the more you get comfortable and familiar with them, and you can spot what the easiest method is going to be. Okay, there's a simple trig proof done. Let's have a look now at a trig equation. So what we've got here is an equation in terms of cosec. We're looking at the range of values for which we want our answer in terms of pi, which tells us we're working in radians. And so what we've got a quadratic in terms of cosec. So here we go. Let's solve a quadratic, which is either the case of banging into your calculator, or if you're old school like me, you'll do some factorising. And there it is, factorised. So now we've got cosec from here. Cosec x is minus 4 over 3. And because you haven't got a cosec button on your calculator, we just need to turn that back into a sine, cos or tan. And cosec is sine. So flip it upside down, we end up with sine x is minus 3 over 4. And that gives us x is minus 0.848. And then it's just a case, and again, I like to scribble the sine curve. So I'm at minus 4 over 3, so we're here. Those two values are outside the range, so I need to consider the two values that are down here. And the way I get at those is by doing pi minus that answer. And so we've got that one there and that one there. Again, up to you how you choose to go about it. I like to scribble a little sine curve like that just so I can see what's going on. And so what we've got there is x is 2.29 in terms of radians. Okay, on the other side, we've got cosec x equals half. Flip it upside down, so that gives us sine x equals 2. And so we can see from there that's not going to lead to any solutions at all, because there's no solution to that equation, because values for sine can only go from 1 to minus 1. So there we go. There's our two answers we have for x. Minus 0.48, 848 and 2.29. Okay, so what we've got there is just two examples of how we can manipulate essentially our 6 ratios, and then also how we can deal with solve an equation involving a reciprocal trig function. Cool. Right, and now last thing we're going to do in this video is just have a look at what the graphs of cosec, sec and cot look like. So again, you need to be familiar with those. And we're going to use that to give a little bit more explanation as to why, when we ended up with cosec equal to half, we got no solution. Right, as I said, we saw on the last slide that cosec doesn't exist for certain values. So let's have a look at the cosec curve and see what happens. Well, cosec is 1 over sine, so let's start off by thinking about the sine curve. And we need 1 over sine, so straight away, let's consider what happens if sine x equals 0. If sine x is 0, we've got 1 divided by 0, so therefore cosec is undefined, doesn't exist. So straight away, that tells us that we've got asymptotes on this curve, and we've got asymptotes at 0, pi, and 2 pi. Right, now, we're starting here, we're saying, okay, sine is going to start gradually increasing, so the value on the bottom of my fraction is going to increase. So as sine increases, that means cosec will decrease. And it will keep decreasing kind of up to a point where we get to pi over 2, at which point if sine x is 1, cosec x is going to be 1 as well. And then as we go down this section of the curve here, sine decreases, the bit on the bottom of our cosec fraction decreases, which means the value of cosec is going to start increasing until we get down to here where sine x equals 0 again, at which point the cosec curve will shoot off the top of the graph. And so we end up with a kind of U-shaped curve looking like that. And if we keep going for values from pi to 2 pi, exactly the same thing is going to happen. Hopefully you can imagine that now, and it's just the same except for the fact it's negative. So what we've got there is that cosec curve is just going to keep repeating those U-shapes that are matched up with the kind of the bumps and the humps on the sine curve. And coming back to the note at the top of the slide, we know that we can't get a value for sine that is bigger than 1 or minus 1. In the same way, you'll notice there's no value for cosec in between 1 and minus 1. Values for cosec of an angle have got to be smaller than minus 1 or greater than 1. Okay, so that explains the result we saw from the quadratic on the previous slide. Okay, sec is going to follow exactly the same structure, except it's the cos curve, so I always find it's just easy when I sketch these things, it's far easier just to have a think about the cos curve first, whack in the asymptotes, there they go, and then put in those U-shapes in exactly the same way, and what you've got there is the sec curve. And if we could continue onwards, you know, this U-shape here would continue up there, this one here would continue if we went past 2 pi up here. So again, we've just got exactly the same shape of the curve as we have for cosec. It's just the U-shapes are kind of just a shifted version of the previous curve. And finally, cot. So there's our y equals tan x curve. Same thing, we've got asymptotes occurring, and they're going to be occurring at x equals 0, pi, and 2 pi, because that's when the values for tan are 0. Let's put those in. And as tan increases, 1 over tan is going to decrease, and as tan goes off the top of the graph here, as the value of tan x tends to infinity, then the value of cot x will tend to 0. And so what you're going to get is these kind of reversed S-shapes. So they're the same kind of S-shapes that we got from the tan curve, but they're just going the other way, and the asymptotes are different places. We had asymptotes for tan at 90 and 270, or apologies, at pi over 2, or 3 pi over 2. That's now where we've got cot equal to 0 at those points. And we haven't got any restrictions on cot or tan in the same way as we had with sec and cosec. We can get any values at all for those. Okay, sorted.